This is the lecture for Friday, March 20th. Today we'll be continuing our discussion of quantum many-body theory. We'll start off with the topic, the anthropic principle. The anthropic principle is the idea that there are parameters of nature that seem to be just perfectly tuned so that life can exist in that universe. And the question then is how could these parameters be just so perfectly tuned? Well, the idea of the anthropic principle is that if the parameters of nature were not perfectly tuned for life, then life wouldn't form, there would be no intelligent beings, and nobody would be around to say, oh, that's too bad. So the anthropic principle is essentially saying that in a universe where the parameters of nature are perfectly tuned, then we have the formation of intelligent life, and then the intelligent life looks back on the universe and say, wow, we were very lucky. And so that's kind of the idea of the anthropic principle. And so Ulf Meissner is a collaborator of mine in Bonn and Jülich in Germany. And here's some work that we've done together. He's written this article here about anthropic considerations in nuclear physics. And so we considered the anthropic principle relating to the Hoyle state of carbon-12. So the Hoyle state of carbon-12, we've discussed this before, is important for the formation of carbon in the universe. And as you know, carbon is essential for life. And without the Hoyle state being very close to the triple alpha threshold, or the alpha plus beryllium-8 threshold, there would not be enough enhancement for the production of carbon. So you can then ask the question, all right, so in nature, the difference between the Hoyle energy and the alpha plus beryllium-8 energy is about 0.31 MeV, a very small number. As we change some fundamental parameter of nature, like the quark mass, the light quark masses, that's, as far as we know, an arbitrary parameter of nature that could be adjusted, and the universe would be perfectly consistent with a different value. Or we could change the coupling strength of the electromagnetic interactions, and that again would be perfectly consistent parameter of nature. So if we change some fundamental parameter of nature, the question is whether the splitting between the Hoyle state and the alpha plus beryllium-8 threshold, if it starts opening up gaps, or does it remain very close to each other? Do they remain very close to each other? So this would be sort of the non-anthropic scenario where it's always sort of close to the threshold. There's some fundamental reason why it stays close. Or is there some fine-tuned universe scenario where there has to be some tuning to make this work? So that's what we looked at in a series of papers here. This work that my group did with collaborators in Germany on the viability of carbon-based life as a function of the light quark mass, dependence of triple alpha process on the fundamental constants of nature, and varying light quark masses and the impact on nuclear force and Big Bang nucleus synthesis. So this last one, I was not involved in this paper though. So we have the quarks form that constitutes the nucleons, the protons and the neutrons, and then we have the alpha particles that come together to form carbon-12, and then we have the burning of the alpha forming to being captured on carbon-12 to form oxygen-16. So the question is that as we change the light quark mass, whether we can sort of screw things up, move the Hoyle state resonance so that either the carbon-12 or the oxygen-16 production inside red giant stars gets messed up, and then instead of having our nice blue marble, we have some barren system that only has basically only heavy elements, and there's not carbon-12 or oxygen-16, or one or the other, not produced enough. Oh, I forgot to tell you what the conclusions were. Well, the conclusions were not particularly strong, but there was some hint that there was fine-tuning in the universe, that if you do change the quark masses more than 5%, it seems unlikely that you can keep the carbon-12 Hoyle state close to the triple alpha threshold to preserve the abundance of carbon-12 and oxygen-16. Okay, here's another example of sort of the fine-tuning of the parameters of nature. Here is an ab initio calculation. This was actually calculations using lattice quantum chromodynamics, which I'll talk about more next week, where they looked at the neutron-proton mass difference. All right. So here are two parameters of nature that were changing. One was the difference between the down and the up quark masses divided by the physical value of the difference between the down and the up quark masses. And here's the strength of the electromagnetic coupling over the physical strength of the electromagnetic coupling. So they were varying around, so here's the physical point here, where the mass differences between the neutron and proton is about 1.3 MeV. And so they're looking at regions where things get screwed up. So, for example, if you're way over here, you end up getting, you have problems with the beta decay, and you change the evolution of the early universe. Okay, so in other words, comparing the neutron-proton mass difference to the rest mass of the electron. And so they're just looking at the sensitivities of the various processes. And here's another work involving my group and German collaborators, where we looked at the alpha-alpha scattering process. So you have alpha particle and alpha particle. These are lattice simulations done on supercomputers. And we looked at the elastic scattering of two alpha particles. So one way to look at scattering is you measure what's called the phase shift. You have some scattering states coming out, some outgoing scattering states, and you measure how much the scattering wave is shifted from what the scattering wave looks like if there were no interactions at all. And that phase shift tells you about the strength of the interaction, whether it's attractive or repulsive. If the phase shift is attractive, if the phase shift is positive, it's attractive. If it's negative, it's repulsive. So here's a plot of the L equals to 0 phase shift, and so it's positive, so it's attractive. And you can see the comparison at next to leading order, next to leading order calculations. The leading order would be the first step, and then next to leading order is the next step, next to leading order is the next step after that, and so on. And here's a comparison with experimental results. You can do the same thing for the angular momentum L equals to 2 phase shifts, the D wave phase shifts, and you can see next to leading order, next to leading order, and the comparison with experimental data. So this is the work where this comes from. And here's another really interesting paper about the almost long lifetime of carbon-14. Here they're looking at, so we already talked about carbon-14. It has a half-life of about 5,730 years, and so that's why it's used for carbon dating. Remember, the carbon-14 is produced in the atmosphere through cosmic rays hitting the Earth's, it hits the atmosphere, and so there's a certain abundance of carbon-14 being replenished in the atmosphere, but once a living organism stops living, the exchange of gases no longer happens, the respiration no longer happens, and so then the carbon-14 starts to decay away. And so by measuring the carbon-14 abundance, you can get a sense of when the living tissue expired. So anyways, but the lifetime of carbon-14, so this lifetime of 5,730 years is really much larger than you might expect just by a simple calculation. In fact, it's like 4 orders of magnitude or more bigger than you might expect. And so the question was why that is. So they did some calculations using the shell model, what's called the no-core shell model, where you allow all of the nucleons to be part of the calculation and you don't freeze any degrees of freedom. They first did a calculation with only the 2-nucleon interaction, and that's what's plotted here. And they found a Gamow-Taylor matrix element which describes the decay amplitude, and they got a rather large value. But then what they found was that when they included the 3-nucleon interaction, the 3 nucleon force, they could actually reduce this to a much smaller value that could perhaps give some hint as to why the carbon-14 has such a long lifetime. Right, so some hints of that, and here's the reference that corresponds with this. And they did these calculations on a Cray Jaguar supercomputer with about 215 cores, for 215,000 cores for 6 hours. Oh, these calculations were, the dimensionality of the space was 1 billion basis states. So here's some nice work related to the fusion of light nuclei. So there's this NIF, what's called the National Ignition Facility at Lawrence Livermore National Laboratory, where they're trying to make fusion of DT, deuterium plus tritium going to neutron plus alpha. And so the way they do this is they have these capsules, which are basically, there's a hollow interior where they have the fuel, the deuterium and the tritium, and then they have an explosive capsule here that they ignite, and this capsule explodes, it goes out, but it creates lots of heat and pressure on the interior, which hopefully then causes the DT to the deuterium plus tritium to fuse. So part of this this reaction requires knowing the cross section of neutrons against scattering on tritium. And so here's a calculation from first principles. This technique is called no-coil-shell model, using a technique called the resonating group method to handle the reaction part of the calculation, the scattering part of the reaction. And so you can see then their prediction that they get, and you can see it's in pretty good agreement with the experimental data, which are all these different error bars here. Okay, with the most recent ones, they seem to be doing pretty well. And that, here's the reference for that, for this PhysRev letter. Okay, so now let me tell you a little bit about how these calculations work. So what are called configuration interaction techniques. So configuration interaction, that just simply means you work in some basis, like a shell model basis. You have prescribed some basis, and then you write down what the interactions look like in that basis. This can be used to describe light and heavy nuclei, as well as then give you quantum correlations and the detailed spectroscopy. So you start off, there's different ways you can work. So you can have something that's sort of from first principles, where you start off with some interactions that are nucleon-nucleon interactions that are fitted to the nucleon-nucleon scattering data experiments to try to explain the scattering processes at that level, at the 2-nucleon level, and then perhaps even trying to describe scattering and spectrum of the 3-nucleon system, like the tritium. Now, then you will try to get to describing then the many-body system using some diagonalization technique, either truncating with some basis states or using some Monte Carlo methods to try to do this this technique. There's a group that uses Monte Carlo techniques to define the basis states. But very often these days, there's an intermediate step where you try to make these interactions more amenable to this kind of calculation, because this requires a lot of heavy lifting, where you have to do billions upon billions of basis states, and you might actually need way more than a billion. You might need like 10 to the 15 or 10 to the 20 or 20 to 30 basis states, which is not possible. And so with existing computers today. And so the idea is to use the renormalization to make the convergence as a function of number of basis states much more rapid. I'll talk more about that in a bit. Now, there are also other approaches, more the traditional shell model approach, where you write down matrix elements that are fitted to give you experimental data after you do this diagonalizations. In other words, you have some matrix elements, you diagonalize the matrix, you get some answers for the observables here, and then if it's not quite right, you make some readjustment to the interactions, and then you try to reproduce the experiments, and then you try to make predictions for the other things you didn't fit to. All right, so these are sort of two different approaches, the ab initio approach and the more phenomenological approach for doing this. But then once you get to doing the diagonalization, you then can get some observables, and from that you can do direct comparisons with experiment, or you can use that as input for other calculations like reaction calculations, or perhaps even to get an effective theory, so a description in terms of density functional theory, which is something we'll talk about next week. Okay, so here's the nuclear shell model. There are various terms that you have in the Hamiltonian. We have the kinetic energy term, okay, and we have the two-body interaction. But what you can do in the shell model, where the shell model you have, remember what is the shell model? You start off with harmonic oscillators, basis states, where we have so this VI here, this single particle VI would be some r squared, or 1/2 m squared omega squared r squared for the harmonic oscillator. You add that to this one-body Hamiltonian, so now you have the shell model one-body Hamiltonians. But then, obviously, if you add it here, you have to subtract it here, but that's fine. So now here's the residual interaction. So that's kind of the idea of the shell model, to start off with eigenstates of this one-body Hamiltonian, and then include these residual interactions, then diagonalize what you get. Here. Okay, so you start off with basis states that could either be good for Jz or Tz. So Jz is the z component of angular momentum, or a z component of isospin. Or you could actually use some basis states that have good values for the total angular momentum or the total isospin. This, however, turns out to be much more computationally expensive. So typically, these Jz, Tz states are used. So remember, these basis states are some tensor product states of a single nucleon state. So this is just some enormous basis set of basis states. Okay, so then you compute the matrix Hamiltonian then in this basis of a body states. You diagonalize the matrix, try to find the lowest eigenstates. Unfortunately, the number of states increases exponentially with the particle number. So if you do a shell model calculation in the FP shell, so remember the shell model basis, so the shell model orbitals, you have the S shell, then you end up having the P shell, okay, and then you have the DS shell, and then you have the FP shell. So that's where we are here. If you do a calculation just only including the FP shell for zinc 60, you get something like 2 billion JZ states, okay. So if you project onto a given value of J0, T0, you can start reducing the amount in this basis by, if you want to try to restrict your calculations in that manner. Now, so how can we get around this problem? Well, one of the techniques is you can not work with a full space, but try to work with a small part of the space. So you can have some the original space, which will be sort of shown here in this Venn diagram. And you can maybe have a subset of the space, a subspace called P. So if you add P plus its orthogonal complement Q, you end up getting the whole space. But what you can do is you can try to write down an effective interaction that only involves states in the smaller space here. Now, in order to do that, you have to do some work with some Feynman diagrams that essentially integrates away or integrates out the effect of this Q space, but it can be done. And there's some techniques called G-matrix techniques, but more generally, these days we call them sort of renormalization methods, where we renormalize, or renormalization group methods, where we try to reduce the effective space of our calculation. Okay, so now there are you can do some calculations working in the shell model, where we have some valence space. So the idea of a valence space is there's maybe some core states that are considered inert, core orbitals, but then there's some valence space in which we do the calculations, where these nucleons are included in our diagonalization approach. Okay, so there's some various ways of getting effective interactions in this valence cluster, in this valence shell model Hamiltonian. One is from the coupled cluster expansion. So we've talked about this before. The idea of the coupled cluster expansion is that we have a certain number of orbitals are filled up to what's called the Fermi level, and then if you have some missing particles in up to that Fermi level, it's what's called a hole. If you have particles and some energy levels above the Fermi energy, these are called particles or quasi-particles sometimes. Okay, and so then you can make some restrictions on how many particles and how many holes you have. If you allow then various interactions of these particles and holes, then you can write down various diagrams describing these things. The coupled cluster expansion is a clever way of only including connected diagrams. Instead of having interactions that are disconnected from each other, where these guys interact over here and these guys interact over there, you only consider things that are they all talk to each other. The diagrams are talking to each other. But then what you do is, instead of just adding those diagrams, you actually exponentiate these diagrams. By doing the exponential, think of this as like doing the exponential of x. You get 1 plus x squared over 2, and so on. When you exponentiate, you'll not only get these diagrams, you get the square of these diagrams that are disconnected from each other, and so on. That's the idea of the coupled cluster expansion, by including some subset of particle-hole interactions with connected diagrams, then exponentiated. When they do that, they can come up with some effective interactions for doing shell model calculations, and then they end up getting a rather good agreement, quite impressive agreement with experiment, and that can be compared with calculations done using a more phenomenological approach. So here's some shell model calculations using more phenomenological interactions. And by the way, these shell model calculations, a lot of these are done by Alex Brown here at Michigan State. These couple cluster calculations were done by the Oak Ridge group. You can see this paper here. Now, another approach, which is actually not that far away from the couple cluster expansion, but the medium SRG approach. So SRG stands for Similarity Renormalization Group. And the idea is, again, to in the similarity renormalization group is to write down some sort of effective reduction in the space. So what you do is you do some transformations of the Hamiltonian in the many-body space and try to make it look block diagonal. Start off with a very large matrix and try to then make it look like a smaller block. In this case, a smaller block, like this. Okay, and then you diagonalize in that reduced space. So here are some calculations using a medium SRG. This is done by the Michigan State group, Scott Bogner and others. So you can see how they get rather good agreement with experimental data for the excitation energies for oxygen 22. The same thing as we saw before here. And you can see the agreement is quite good. In fact, you might notice that the agreement with a couple clusters is also quite good. So these calculations are quite similar to each other in some sense. Okay. If you're wondering all these different labels here, this is many-body perturbation theory. That's another approach using many-body perturbation theory. This is a medium similarity renormalization group where they don't include the three-body force fully. They don't have an initial three-body force, but this IND stands for induced, meaning this is getting very technical, but they don't have a three-body interaction, but they induce a three-body interaction after going through this process of writing down the effective interaction, where this full calculation includes the three-body interaction from the very beginning and includes all effects at the three-body level. Okay, and so here's some calculations using the various shell model calculations. Here's more phenomenological interactions. So here, as you can see, what's called the Galimov-Teller strength. So this is related to the beta decay transition using. So the experiment is done using a charge exchange reaction where you have the deuteron, okay, which has a neutron and a proton in it, but then helium-2, which maybe looks kind of funny, that's just two protons essentially coming off. All right, and so this charge exchange, what you have is the deuteron comes in. And then what happens is the deuteron gets exchanged for a proton, but then you see essentially what you've done is you've done beta plus decay, where essentially you can think of you've taken away a proton and you've inserted a neutron. So you can see that's related to the beta plus Gamow-Teller matrix element here. Okay, and so this is at 171 MeV. You can see the Gamow-Teller strength as a function of the excitation energy. And you can see these peaks here. And you can see very nicely these peaks correspond with what you see for the states you get, the Gamow-Teller strength from a shell model calculation. It's quite nice. All right, and now here's a calculation by the Otsuka group in Japan, in Tokyo. And these calculations they're doing shell model calculations as a function of neutron number for the excitation energy, the excitation energies that you get in comparison with experiment, and so you can see it's doing pretty well. Here you can see various peaks at various places that are agreeing with the experimental values. Now here then is a sampling of the size of the space for your many-body calculation versus the number of neutrons or number of protons that are equal to each other. You keep them equal to each other. And so you can see it grows exponentially. There's some various kinks here. This is just doing different shells, the FP shell, FPG shell, G9 half shell, FPGDS shell. Okay, as you can see, these are tremendously large spaces, so at some point it becomes rather impractical to do a full calculation. So I'll stop there, and we will pick it up next time. We'll talk about density functional theory, and I'll see you then.